A linear group is a subgroup of G and K. K here is local field, and when I say so G and K is topology, subgroup, otherwise said closed subgroups, and I want to consider now compact solution. And so I want to first discuss the case of groups over the reals. Any compact group in G and R in the blank. More precisely, A in G and R compact exist G in G and C such that H is the K points of G. Algebraic. Precisely. Or, if you wish, it means that I can find real polynomials such that H is precisely the zero set of these polynomials in GLM. Right. So some of you probably know this theorem, right? Who have seen this? Not so unuseful. Okay, so this is very basic. So take V to be M and R. As usual, I'm kind of more and more I will not be that formal. I will confuse myself and you yourselves between real points and variety and the variety itself. Now G act on V by left multiplication. So this is a G variety. G itself,
wait, G is here. I certainly want to prove that G is H is.
Okay, I call it H, and I hope. Okay. Let O be the orbit of 1 in V. So this is the copy of the group. This is a set, but I want to think about it as an orbit in that bigger variety. And I want to find polynomial that this is a zero set of those. Right? It is obvious what would be the idea of polynomial that this is a zero set of those if it is a zero set of any. It would be the idea of polynomial that vanish on this, of course. So, so we define I to be all polynomials that vanish here, and Z to be the zero set. So it's all V in V, such that for every F in I, F V we want to establish this equation. fixing another edge orbit, and I want to show that so actually what I want to do is to find a polynomial that vanishes on O and is a G-invariant polynomial. Actually, I want to find a polynomial that vanishes on O and does not vanish on O prime. I will find a G-invariant polynomial which obtain different values of those. So by just adding constant, I'll be done. So to start with, I'll find not polynomial. So I'll use two properties of the rings. One is not a property of the rings, one is property of this of the compactness of these two sets. I can separate compact sets by continuous functions. This is the normality of the vector space V. And then I will use Weierstrass theorem to say that every continuous function could be approximately uniformly on compact sets with polynomials. So this is a property of the rays. And so the theorem that we're discussing is not true over other fields. On any other field, it is not correct. And then I will have to once more. Okay, let's start. So then we'll see what happens. So by normality, I can find phi, a real valid continuous function on V, such that phi at O is less than 0 and phi at O prime is more than 1. Actually, this is strictly less. This is less than minus epsilon for some epsilon, the compactness, right? Of O. And this is more than 1 plus epsilon for some epsilon. So by Weierstrass theorem, I can find f a polynomial in V such that f at O is less equal, say, 0, and f at O prime is more than 1. Now I want f to be 0 here. To begin with, I want f to be constant here. This would be the case if f was G-invariant, H-invariant. So I can just average f, average in the space of polynomials. F, we can average f. F with respect to normalized Hauer measure on H. So f prime at any V would be, so I'm defining f prime now. Would be, or maybe, let me write first just a symbol. H. And let me explain what it means. F prime at a point V will be, so we'll take F, we will translate it by H, so it will be H minus 1, and I will, this is a number, real number, and for every V, H being varying on some compact variety, this will be a compact set of numbers that I'm getting. I can average it. So f prime, so each of these symbols is a shifted polynomial. It's a polynomial of the same degree as f. Right? Each of these symbols in the variable v. And now I'm just, if you want, I can approximate this sum by some finite sum of thick enough finite net in H. So this would be a polynomial of similar degree, and well, take the limit in the space of polynomials. So f prime is a polynomial of the same degree as f, which is H invariant. Now, f prime restricted to O is some constant. Less than 0. F prime restricted to O prime is constant. I don't care much about the fact that it is a constant actually. It is more than 1. Because I average values which are all more than, less than 0 or more than 1. So shifting of f prime minus c is in I, f prime minus c at O prime is not. Hence, points of O prime are not in 0. But O prime was arbitrary. Every point, I guess that I could just, I didn't need to consider O prime, I guess that I could just take a point. Maybe, let me change point. U not in. It doesn't matter. Just a nicer way to write down. Sorry for the mess.
You do want phi to be more than 1 on the entire orbit.
Yeah. This, okay. There was a reason I did. So, thanks.
Can you repeat why f tag is a polynomial?
Yes, I mean it's a uniform limit of polynomials. Of the same degree.
Ah,
Of the same degree. Oh, sorry for that. It doesn't do. Done. Okay. No.
I have a question. So why doesn't this walk over C?
Exercise. Every algebraic group in G and C, every complex algebraic group is compact, it's actually finite. I don't know if it exactly answer your question. This is the fact. It's a correct fact. I'll give you a hint. Every solvable group splits over C, right? It should follow from what we've seen. If you have a higher dimensional group, it will definitely make more than 0. It will contain split subgroups, as it cannot be compact. So this is the fact. What actually failed was sorry? Yes. So if the analog or the relevant counterpart of Ashe's theorem for complex valued functions requires conjugations. Right? So yeah, is that. Okay. What about? Oh, okay. So, but every complex group I can think of as a real group. So still I get a lot of information about compact group in GL and C. Just think of GL and C as a subgroup of GL2 and R, and a compact group in GL and C is a compact group in GL2 and R, and must be algebraic as a real group. Okay? So I do have some understanding due to the theorem for those groups. But it's really, I mean, even if I care about complex linear group, I must consider the real in order to use algebraic geometry. This is really a fundamental fact. Now, the following theorem is something I will not really discuss here, but for completeness, I hope to come back to it. For completeness, I will discuss a linear group over non-Archimedean fields. So, K is non-Archimedean local field. G in G and K compact. Then G is cofinite. So do you know what profinite group is? A group is called profinite if it is isomorphic as topological group to an inverse limit of finite groups. I'll give a few examples now. So again, this is not what I want to discuss in full now. I hope to come back to it as well. Here's an example. Take Z mod B. Z mod B squared. So what is this group? This is the periodic integers, right? So of course, an inverse limit of finite spaces, always an inverse limit of compact spaces, is compact itself. So profinite groups are all compact. A connected group cannot be a profinite group unless it is trivial, right? Every topological group has the connected component of identity, and every topological group G has G0, normal in G, characteristic, as topological group, and G mod G0 is totally disconnected. It has no connected component of the identity, nor of any other point, as all points are alike. If so, in particular, so claim. Oh, maybe I want to give more examples. Just okay, I'll prove the claim. Claim G compact totally disconnected imply G is cofinite. So this theorem here is really not about non-Archimedean fields. It's more about general theory of compact groups. Model of the connected component, they are all profinite. Compact groups are profinite. So finite group theory somehow controls finite group theory and Lie theory of compact Lie groups, algebraic groups over the reals, controls all compact group theory. Sketch of the proof. So we know that G is a basis neighborhood of identity consisting of Klopen sets. Sets which are open and closed. Right? So this is general topology. Every totally disconnected compact group has this property. It has a basis of neighborhoods which are open and compact. So this is an exercise. It's not triviality, but it's not hard. We need to show that we have a basis of neighborhood of identity consisting of normal Klopen standards. Right? If you have a subgroup which is normal, I can take the quotient, and if my group G is compact and N, the normal subgroup, is open, then I have only finitely many cosets, right? Because they form a cover. And so the quotient G mod N is finite. And if I have a basis of neighborhood consisting of such N's, then my G can be seen as the post-finite completion of these G mod N's. Right? So this is what I want to establish. Now let me take an intermediate step and I have to show that at least basis of neighborhood of identity consisting of Klopen subgroups. Same, but without the normality. So this is, again, the standard thing. If I have any open subgroup, any group, if you have H in G open, it is a finite index by the same reasoning as before. I want to show that H contains actually smaller group N, which is normal as well. finite index subgroup of H. This is a standard thing. N would be just the intersection of all conjugation of H. If you want, I can H in G finite index, being open clarity is finite index. Then I can look at G mod H and let G act on it. So this is symmetric group of some finite order, and I will look at the kernel of this one.
Doesn't
Yes, this is the kernel, unless G is finite. So you have some kernel to it, and the kernel will of course be open. And open and hence closed, and this will be my N. This is how to move from here to there. So explain how to move from here to there. I guess I need to move from here to here, and this we know already. At least so I claim. So now I want to explain this statement and be done by that. So take any set like that. I want to take V open neighborhood of identity, closed neighborhood of identity. I want to show that I can find in V H closed neighborhood sub of identity. So find first U open neighborhood of V such that UV is in V. Let me explain. For any point in V, V is open. So for any point, there is an open neighborhood of identity that if I multiply the small v and open this point in V by U is small enough, I'm still in V. This is by the fact that V is open. So I can cover V by such things. But V is also compact. So a finite cover will suffice. So I can find U's which will do it uniformly to any point. Okay, so this is a fact. So actually it will be open. Actually, of course, since one is here. Since one is here, I will have a quality. And U is U inverse. Maybe take the intersection of U and H inverse. Big set, a bit smaller U. And now take, or maybe observe, maybe emphasize U is in V. It follows, but observe that U to the N, so this is the product of words of length N that I can find in U, is always in V by induction. U is in V, and U times U is in U times V is in V, etc., etc., etc. So H, which is the union of all UNs, closed, is in V, since V is closed. So this is a group. Is a group. Clopen. It's clopen because it contains an open neighborhood of the identity. So it is open. It's closed. It's a clopen group containing it. Okay, so this is a classic experiment. So I gave a sketch. It has nothing to do pretty much with linear group theory, but I accept the fact that it is very useful to prove this theorem because our group here has no connected component of the identity here. Right? Everything is totally continuous. I guess I want to give some more examples. I can take maybe an example which is not linear, or at least not linear over any unique local field, is the following. Take the example of all z mod n's, when you have z mod n to z mod n, if n divides n. So this is a direct system which is not linear. And the inverse limit of this will be C hat. This is the profile population of C. Every group, here I looked at Z and all its finite portions, and I took the inverse system correspond to all, and Z embedded in these. Whenever a group is residually finite, every element survives some finite portion, to embed in that inverse limit, which is called the profile completion. And just maybe I should make that now. So this is a compact group, and it's the product of all the ZPs. This is the Chinese reminder here. Now, I gave these two examples. I will not give essentially other examples. I can just boost them by taking group over those things. For example, I can look at SLN Z mod e to the k, the inner system associated with this, and here I will have SLN CP. Of course, this is a subgroup of SLN QP. This is a compact subgroup of this linear group. Okay? Somehow, okay. And this actually is known, and I will explore this fact pretty soon, that this is the maximal compact subgroup of this group, and every semi-simple group over a local field has finitely many maximal compact subgroups, which are all finite, of course, and all come from, they're all linear over some ring. And every other compact group is actually contained up to conjugation in some space.
So is it clear that the profiling group cannot be algebraic?
No, a profiling group can be algebraic, but this is not algebraic. But
Yes, so there are compact.
there are compact groups which are algebraic. And actually, I gave you a recipe how to construct such. Take QP star, for example. Sorry. Take a finite extension of QP. Take the star of it. Think about it as a group of QP to do restriction of scalars. You have to divide now by some torus that you will see them, which is split, coming from QP star, the coming from QP itself. Divide by it, you will get an unrestricted torus. Over the periodic, it will be a torus. We've seen that over, I said that over fields of characteristic P might be unipotent, somehow it might be. Okay, in any case, you will get some computation.
Do they have a name? This construction.
Unrestricted torus. I don't know, maybe they have more names. But also you can, instead of starting with field extension, you can start with division algebra. So it is a fact that compact groups somehow do come from division algebras. In a certain sense, and again, algebraic ones. I'll explain this. Am I now? I'm about to finish, don't worry, just want to see it. Okay. So, this is the explanation. there is a lecture by Elon, you know.